Welcome, everybody. First of all, I would like to thank the organizing committee for the invitation. Today, I'm going to talk about graph neural network with learnable, structural, and positional representation. This is a joint work with Vijay Dwivedi, Luan Tuan, Thomas Arendt, and Joshua Banjo. So here's the outline of the talk. I will briefly review GNN architectures. Then I will talk about structural and positional representation. And then from there, I will introduce graph neural network with learnable positional encoding. And finally, I will conclude. So graph neural network have become the standard toolkit for analyzing and processing data on graphs. So this is one of the hottest topics this year in the community. So the success of graph neural network is due to its flexibility to adapt to diverse domains like chemistry, physics, recommender systems, social sciences, knowledge graphs, neuroscience, computer vision, NLP, and combinatorial optimization. So there has been a decade of developments of graph neural network architectures for real-world adoption of these new techniques. So there exist two main classes of GNNs. The first one is message passing GNNs. I also call them graph convolutional networks because they are direct extension of convnets from images to graphs. And they are today the most commonly designed architectures. Then we have Westphaler-Lehman GNNs. They are GNNs based on the isomorphism test. They are recently proposed architecture from 2019. They are theoretically grounded with expressivity power and universal approximation, and their motivation is to go beyond message passing GNNs. So GNNs have been designed with the expressivity power to distinguish non-isomorphic graphs. What is a graph isomorphism? So if you have these two graphs, they look like different, but they are actually the same. You can find an index permutation which will preserve the node adjacencies. The Westphaler-Lehman test, the WL test, provides a necessary condition to guarantee that two graphs are isomorphic. So they are the same. GNNs were designed to be as maximally as expressive as the original WL test, but the original WL test can fail to distinguish sometimes some simple non-isomorphic graphs like these two graphs here. So we need more expressivity power. For this, so Maron, Lippmann, and their collaborators, they develop a new GNN based on higher order interaction between the nodes. So if you take the original message passing GNN, the interaction between the nodes are pairwise, so there are two tuple of nodes. If you consider more interaction like between three nodes, then you will consider three tuple of nodes. When you do that, you are going to increase the memory and the speak complexities. And the thing is, we need at least k equal to 3 to be theoretically more powerful than message passing GNN like GNNs, which make this GNN less practical. So there has been this recent development with 3W, ring, and 2FGNN, where you get the best possible memory and speak complexity for this class of GNNs. So WL GNNs are permutation invariant universal approximators, which means that they can approximate any continuous function that are permutation invariant, but again under the condition that you will use higher order tensors. And what we showed last year in a benchmarking paper is numerical performances of these WGNNs are actually not necessarily better than the traditional message passing GNNs. There have been some recent works by Michael Bronstein and his collaborators which present hybrid WL and message passing GNNs. In this technique, they use some prior information about the class of graphs that you want to process. For example, we know for molecules that we have rings, so cycles, and for social network, we have cliques. So based on this structural information, they can design a new message passing GNNs, which are quite performant on molecular datasets. So for the second class of GNNs, we have message passing GNNs. So what are the properties to design this class of networks? So we need invariance with respect to node permutation. We need to be independent with respect to the graph size and the neighborhood size. We also want to have locality, so we only want to consider neighbors. We also want to have weight sharing to emulate graph convolution. And finally, we have linear complexity with respect to the number of edges, which reduces to linear complexity with respect to the number of nodes for real-world sparse graphs. So when you have these properties, you actually are quite limited on what you can do. So the representation of the node I at the next layer will only depend on the representation of the same node at the previous layers and its neighbors. The flexibility that you have and is actually, the number of possible function f is the number of papers published in the literature. So here are some message passing GNNs. So for example, spectral GCN that we developed earlier, which are based on Fourier theory to generalize convolution on graphs. And for these GNNs, there is actually a misconception that they are not generalizable and computationally expensive, which is not true theoretically and numerically. Then we have spatial GCN, which are, as I said before, the most commonly designed GNNs. For example, you have GCN by Keith and Welling. You have also GraphSage by Hamilton, Ying, and Leskovec. GAT by Peter Velikovic, Joshua Benjo, and their co-author, and recently we introduced GraphTransformer. GCN leverage graph sparsity, which is a very important inductive bias when you want to generalize to new graphs. The node update equation is local, which means like as a traditional convnets, you can parallelize the operation. But here you need to consider sparse matrix multiplication. So you need some specialized library like DGL, PyTorch geometric, or spectral. Finally, GCN benefit from batch normalization and residual connection. But these message passing GNNs, theoretically, they have limited expressivity power. And the reason for that is they are unable to distinguish some nodes because either the message passing function is not discriminative enough. So for example, if you consider the max and the mean discriminative, the max and the mean message passing function, if you take these two red nodes, they cannot be distinguished by using this message passing function. So you have a limitation due to the aggregation function. Another limitation is we have for any graph existence of natural symmetries, like for example isomorphic nodes. So if you take this hydrogen atom and this one as well, so they have the same neighborhood. So the message passing GNN will basically provide the same node representation for these two atoms of hydrogens, which is a limitation because you want to be able to distinguish these two nodes. So how can we overcome this limited expressivity power in message passing GNNs? So as I said before, we can consider higher order node interactions. So instead of just looking at pairwise nodes, you can also look at k-tuples of nodes. And this give us the WL GNNs, which are computationally more expensive than message passing GNNs. An alternative is actually to provide a unique identity for each node. So a unique positional encoding for each node. So there have been some theoretical results on that. So if you take theorem from Ribeiro and his collaborators, so they prove that message passing GNNs are more expressivity power if you consider node positional encoding. And also the theorem from Lucas basically say that message passing GNNs are Turing complete if each node is uniquely identified. So what positional encoding? So the simplest positional encoding we can think about is to have an indexing of the nodes, you know, like this node will have index 7, index 6, and so on. But this is a choice among, you know, n factorial possible ordering of the nodes. So what you do in practice, because you want your network to learn this invariance with respect to this node ordering, what you will do is that you will uniformly sample among the n factorial possible choice. But this will be an approximation at the end. So what are properties for designing a good positional encodings? So you need a uniqueness of representation for each node. You need to be permutation invariant. And you want your positional encoding to be distance sensitive, which means that if you have two nodes close to each other on the graph, you want the distance between the two positional encoding to be small. And if the two nodes are far away on the graph, you want the distance to be large. So for this, we proposed last year Laplacian positional encoding. So they are based on the Laplacian eigenvector. So they are spectral technique that embed graphs into Euclidean space, and they form this way coordinate systems that basically preserve the global graph structure. They are defined via factorization of the graph Laplacian matrix. So which is here, you have the identity minus, this is the degree adjacency matrix. If you do the factorization, you will get the eigenvectors, and here the eigenvalues, and eigenvectors are the positional encoding that we used last year. So they are interesting because they are hybrid positional and structural encoding. They have unique, and they are also distance sensitive. And also they are a natural generalization of the standard transformer positional encoding, so the cosine and sinus functions, but here defined, generalized to graphs. So there is a limitation with this Laplacian positional encoding. Laplacian eigenvectors are actually defined up to the sign, plus or minus 1. If you have k positional encoding Laplacian eigenvectors, so this is going to be the number of possible sign flips 2 to the power k. So again, we don't have any choice in practice. What we do is that we uniformly sample at random, you know, the signs of the eigenvectors in such a way the network will try to learn this invariance. Fortunately, we don't need too much eigenvectors, which is much smaller than the number of nodes. But still, this is a limitation. And despite this limitation, actually, this Laplacian positional encoding have good performance in practice. They have been used in our recent work with GraphTransformer, but also in other works with Decade GNN and SAN. And other, I want to mention that other graph positional encoding exist. All right, so let us now define graph neural network with learnable positional encoding. So currently, existing GNN inject the positional information into the input layer of the graph neural network, much like for Transformer. So you have the node update equation here, you have the age update equation because you have graph, and the input is going to be a linear embedding on the concatenation between the input node feature, like the atom type for molecules, and here the graph positional encoding. What here in this work, what we propose is to decouple structural and positional representation to make easy for the network to learn structural and positional information. So we're going to have the node update, the age update, and we're going to have a new update, which is the positional encoding update, okay, with the variable P. And P will be used in the age update, the structural update. So there are different possible GNN. Let's take one, which is our previous work, Decade GCN, and let's augment it with learnable positional encoding. So here is going to be the same architecture as the original GNN, but we are going to augment it, with positional encoding, so which is P. And what we will do is that each time we have a structural vector here, we are going to concatenate it with a positional vector here. Okay, so we have structural information, positional information, structural information, positional information. So that's quite easy. And then we will update the P in such a way that will be equal to P plus tangent hyperbolic, because here we let positional vectors to be positive or negative. And the equation here will be the same analytic form than the one for the H vector, the structural representation. Instead, we have some new parameters to learn for this P. And also because we want to encourage to have a coordinate systems, we're going to have the mean of P with respect to the nodes to be equal to 0. And we also want the unit norm of P to be equal to, the norm of P to be equal to 1. Okay. So since we have some positional representation, we can also add a positional loss. So for example, a very natural one will be, okay, let's add the Laplacian eigenvector loss such that the positional encoding will form a coordinate system constrained by the graph topology. So at the end, the final loss will be composed of two terms. We're going to have the task loss, so the standard one, but the input will be, the structural representation and also the positional information at the last layer of the convnet. Plus this positional loss, here we use, again, the Laplacian eigenvector loss. So this is here the Dirichlet semi-norm, where you have P times the Laplacian times P. And here you want P to be a coordinate system, orthonormal coordinate system. So P transpose P is going to be the identity matrix. Oops, sorry. So we can also use this learnable positional encoding for other GNNs. So, for example, here we consider PNAH from Peter Velikovic and his collaborators. So, again, we can augment this GNN architecture by concatenate, the structural information with the positional information here and here. We keep the same aggregation equation. We have the new P update with here the same analytical form as this one, except that we have different parameters that we can learn. Yeah. Numerical results. So we did the implementation using DGL, and we will release soon the code on GitHub. So this column is going to be the number of parameters, the number of layers. This is the test accuracy, the lower the better. This is the train accuracy. This is the number of epochs, the time per epoch, and the total time. So this is gated GCN without any positional encoding. The performance is 0.25. This is gated GCN plus Laplacian positional encoding. We can improve significantly 0.20. And if we learn the positional encoding, we would get 0.09. Which is a significant improvement. Then we can also add this positional loss, and as you can see, we improve a little bit on standard deviation, but we don't improve the overall performance. This is PNAH. The performance is 0.14. If we had this learnable positional encoding, then you can improve to 0.10. So we can see that we can improve message passing GNN architecture by adding this learnable positional encoding. Something surprising is that we don't actually improve the result when we had this structural loss of Laplacian eigenvector. So we might want to use maybe different losses. All right. So there exists some limitations with standard message passing GNNs. which are the long-range dependencies. So if you want two nodes to communicate to each other and they are far away on the graph, then you will need a lot of layers to do that, and you may have the vanishing gradient problem. Another problem is over-squashing. So that was identified by Alon and Gahav, is basically that, if you want to get representation of this vector, it will aggregate the information of all the layers. So, so this is actually worse than RNNs, recurrent neural network, because you just have a line graph. So Transformer may solve these issues by making everything connected to everything. Okay, but you will it will require to trade the linear complexity of sparse message passing GNNs with quadratic complexity, which means in practice that we are going to be limited to small graphs like molecular graphs. And we will not be able to apply this technique to larger graphs like social graphs or knowledge graphs. So we did that already last year, and GraphTransformers actually have poor performance on molecules. So a direct use of the transformer to graphs doesn't really work well compared to other competitive techniques. So there are more which is needed to make this work, and that was actually presented recently in some recent paper, transformer-based GNNs, which are quite promising with SAN, Graphity, and GraphNormer. So here is the standard transformer architecture. So this is the next layer, the previous layer. The input layer is going to have linear embedding of the node inputs like the atom type plus positional encoding. And here you have the standard transformer layer, layer normalization, multi-layer perceptron, and multi-head attention. Multi-head attention where you have the attention mechanism here, where you have the softmax, the query, key, and times the value. So this is in matrix representation. If you look at in a pointwise representation, basically you're going to have Wij, the weight score, and the weight score is going to be exponential of the attention score, and the attention score is going to be the inner product between the key and the query. So we introduced GraphTransformer by having the idea of consistency with standard transformer, as I'm going to show you here. So basically, we want the GraphTransformer to reduce to standard transformer under some conditions. So for GraphTransformer, we need the edge representation. All right. So we had an extra update function for E, and the multi-head attention will depend on the edge feature. Okay. So we know that for molecules, we have some bonds connection between nodes, and we want to use this information. So the difference with standard transformer is that here we are going to do the sum over the neighborhood of the node, and in standard transformer it was done on all the nodes. And for the attention score, we are going to use a bilinear product. We are going to have the query diagonal of the edge feature and then the key. So if we consider that the edge feature is 1, so no particular information, and the neighborhood is the set of all nodes, then this reduces to the standard transformer. So that was the consistency we wanted. But again, it didn't work. So there have been some follow-up works, very promising. So like SAN, where they proposed to separate parameters for edges, the true edges, and then the complementary edges, so the non-existing edges. And they did a weighted additive contribution between edges and non-existing edges. Then there has been a Graphity, which using diffusion geometry to capture short range interaction between nodes and long range interaction. So which is here. So what they did is they multiplied to the weight score, they multiply by the diffusion distance. So if two nodes are close to each other, the diffusion distance will be equal to 1. And if they are far away, this will have a small value. So it's going to naturally weight the weight score by the topology of the graph, basically. Then we have GraphNormer. So this has a very similar idea that we want to add some pairwise interaction between the nodes inside the attention mechanism. So here they did it by adding in the attention score an extra term, which depends on the shortest path between I and J. Yeah. So what we did here is to improve SAN by adding some learnable positional encoding. Very easily, so we had this positional encoding here, also in the multi-head attention, and we have the P update where we are going to use the same aggregation equation as this one with different parameters. Okay. What we did also is, so there is a weighting parameter. So this is the weight score. The weight score where you have, attention mechanism for the IAJ, for the edges, for the existing edges, and this is for different edges. So you're going to have different weighting given by gamma, and in the original paper it was fixed manually or by cross validation. Here we just learn the gamma by backpropagation. Okay, and again, so each time you have the structural information for the query, the key, and the value, we just had the structural information. We also augment graphity by adding this learnable positional encoding. And we also separate the parameters between edges and non-existing edges. Okay. So again, you're going to have here the diffusion distance, Kij. We're going to have the edge feature, and we're going to have the positional information that we add, we concatenate to the structural information. So these are the numerical results. So here you're going to have the fully connected GNN, so the transformer-based GNNs, and here the sparse GNN. Okay. So if you take the standard transformer, the performance is not good, is 0.72. So remember, the lower the better. If you add the Laplacian positional encoding, you're going to improve the performance, but it's still not so good. If you look at, for example, GraphNormer, the performance is quite good with 0.122. If you look at SAN, the performance is also good with 139. If you had this learnable positional encoding, then you can improve even further the performance, 104. This is graphity, the performance is 196. And if you add this learnable positional encoding, you can improve to 106. So adding learnable positional encoding actually improve transformer, SAN, and graphity. Something that was surprising is that so the performance coming from sparse GNN was actually slightly better than the performance coming from transformer-based GNNs. And remember that the time that we need is much smaller because it's linear complexity with respect to quadratic complexity. Conclusion, so decoupling structural and positional information inside the GNN is actually a way to improve performance. Empirically, they are good for sparse and also fully connected GNNs. Initial positional encoding is important and should be based on diffusion geometry like random walk. And for transformer GNNs, it is critical to separate actually parameters between existing edges and non-existing edges. So that was a very good idea from SAN. And surprisingly, transformer GNNs originally designed for to overcome the long range interaction between nodes and also over squashing actually does not beat sparse GNN here. So there is something interesting. And thank you very much for your attention.